So wrapping up the end of the part 1 video, we have a graph that looks like this, and we know that the curve is going to grow really, really quickly this direction, and when we come this way, it's going to get closer and closer to the x-axis. But it's never going to touch the x-axis, and it's never actually going to be a horizontal line, even though that's what it looks like. Then it asked us to graph the other one, y equals 1/2 to the x, but what I'd like to do is graph the one that's in, one of the ones that's in your notebook. So let's do what's number 3 in yours?
Y equals,
Okay, do you have one that's y equals 0.8 to the x?
Yeah.
Okay, let's do this one because I think it'll be a little bit easier for us to graph. So is this growth or decay? Decay because?
It's greater than 0 and less than 1.
Because 0.8 is greater than 0 and less than 1. So we're going to go ahead and graph this. I'm going to move my y-axis over just a little bit. I'm going to leave my x-axis there. So draw yours where it is. It asked you to say whether it was growth or decay, so you're going to say it's decay. Decay. Because 0.8 was less than 1, but it was also greater than 0. What 2 ordered pairs do we know are going to be on this graph?
0, 1, and 1, 2.
Uh-oh. 0, 1, and 1b. What's b? 0.8. 1, 0.8. So if I plot 0, 1, and right here. And 1.8 is like here. Yeah, let's try further out. Let's try like 4. Yeah, what if x is 4? Plug that in on your calculator. What is 0.8 to the 4?
4, 0, 9, 6.
Okay, so about 0.4, just under a half. So if I go over 4, come down here. What about where x is -2?
Yeah.
6.4. So we're going to go up 1, 2, 3, 4, 5, 6. What? Okay. So see how high it is up here and how low it is down here? That gives us kind of a good idea of our graph. Wow. These drawings are not going to be great, but that's why you need to have your points on there where they're easy to identify. And then I know you know what you're trying to graph, all right? Okay, so we can graph it, we can identify if it's growth or decay. This is something you need to add into your journal. So you have that big open space at the top of page 29. I would put this there. So I'm going to give you a second to write that down. So these exponential and growth models are variations of the model we were just talking about. The parent function was y equals b to the x. So you can see that this right here is representing b. Now your exponent is a t, and that's because for these models, t is time. So instead of using x, we're going to use t for time. Y is the amount of stuff. So what that means is things like, if you have bacteria, bacteria grows at an exponential rate. So if we're talking about bacteria, y is going to be the amount of bacteria that we have. And then R is the rate of growth or decay. So it's the percent increase or decrease depending upon what's happening with your substance, whether or not it's growing or it's decaying. So this is number 5 in your journals. I think it's on page 31. It says the number of bacteria Y which is in thousands, in a culture can be approximated by the model y equals 1,000 times 1.99 to the t, where t is the number of hours the culture is incubated. So what is the 100, do you suppose? Well, the base itself is this piece in here. 100 is the amount that you start with. So this means that in this example, we start with 100 bacteria. Is this going to be exponential growth or decay? Growth. And we know it's growth because 1.99
is larger than that.
perfect, is greater than 1. Now, part B says for us to identify the hourly percent increase or decrease in the number of bacteria. So that means we want to know what is R. Now remember, in the form, it says 1 minus R or 1 plus R to the T. So if 1 plus R is 1.99, what is R? 0.99. So if I just do 1.99, get rid of the 1. So the percent would be 99%. That's a very large growth rate, right? Now this says estimate when the number of bacteria will reach 1 million. Now our Y is in what? So 1 million is how many thousands? 1,000. So we want to know when Y hits 1,000. What would T be? So T is an exponent, right?
Yes.
And at this point, we've not learned how to solve for a variable if it's in an exponent form. Okay? So for this, put a big star and say graph. We're going to need to graph this on our calculators in order to figure out when it hits that number. We're going to use the graph to solve. I'm going to grab my calculator and I'm going to type in to y equals what my equation was. So hit y equals on your calculators. Also, when you're doing this, make sure that none of these plots, plot 1, plot 2, plot 3, are highlighted. If they have a black outline around them, that's not good. So you need to turn those off if they're on. Our equation looked like 100 times 1.99 to the x. You need any help with finding the buttons? It's right next to the alpha key. Mine is red. X, T, theta, and something else.
Can you also do alpha and then
I would recommend that you not. I would just use the X key. And then we want to know when y equals what? 1,000. So I'm going to put in a second equation, y equals 1,000. Now since that's just y equals a number, it's going to be a horizontal line when we graph it, right? So we have our curve that's growth, and then we have our horizontal line. Now when I hit graph, okay, so I'll look at that. But before I get there, can I see it on here?
No.
Because what is my window?
Oh, it's 10.
Yeah, I'm only going as high as positive 10 or as low as negative 10, and I need to know where it hits 1,000. So I'm going to hit window. The window button up there at the top allows me to change what I want. And I want Y, so see my Y max? I want it to be 1,000, but I'm not going to make this number 1,000. I'm going to make it a little bit more than 1,000 so that I can actually see it. I'm going to make it like 1,100. Well, we are, but in terms of thousands. So it said 1 million, but Y was in thousands, so 1 million is 1,000 thousands. So I'm going to pause this for a second and then I can look at your graphs. Okay, so if we want to know where our blue line hits 1,000, we want to know where those two lines intersect. Yes, so in your notebook, in your journal, write down these keystrokes. You're going to hit second and then the calculate button. So write those down, second, calculate. This is to find the intersection. So once we hit second and calculate, if we look at the list that it gave us, we're going to choose number 5 for intersect. For this, it's going to ask you 3 questions. It wants a point on the first curve, a point on the second curve, and then it asks if you're ready for it to guess. It does that because we can graph lots and lots of lines on here, right? There's like 8 different lines we could graph. We have to tell it which ones we're talking about, but we only have 2. So we can just hit enter 3 times because the answer to our question is the same every time. So this means x is about 3.3 when y is 1,000. So estimate when the number of bacteria will reach that when the time is 3.3, and time is in what? Hours. So 3.3 hours from the beginning.
Wow, that's really
So we go from 100,000 to 1,000,000 in 3 hours. Yeah. Okay. The next thing we're going to do is talk about writing recursive rules for exponential functions. So that's just another way of writing the rule. Okay? But it looks really obnoxious when you read it, I think. It says an exponential function of the form f of x equals a times b to the x is written using a recursive rule as follows. So f of 0 is equal to a. What does that mean? Well, that means if we have f of x is equal to 3 times 2 to the x. You don't need to write this part down. We'll practice it together in a second. Then f of 0 means we plug in a 0 for x. What's 2 to the 0? 1 times 3 is. So no matter what your function is, if it's in this form, then when x is 0, f of x is just going to be a. Because if I have a times b to the 0, what is b to the 0? 1, and a times 1 is a. So the first thing they say is that if x is 0, the function is equal to whatever a is, the coefficient right there. Then this is where it gets funny. F of n is equal to r. What was r? Yeah, that percent of increase or decrease times f of n minus 1. What does n minus 1 mean? If n is 10, what's n minus 1? 9. If n is 7, what's n minus 1? But it's what number? The number below it, the number that comes before it. So to find something, to find a value here, you do r times the one that came before it. Okay? So for example, this one, y equals 6 times 3 to the x, can be written, and we're going to follow this exact pattern. F of 0 equals 6, because f of 0 equals a, and a is 6. F of n equals r, which is 3 times f of n minus 1. Okay, let's practice this skill. We're going to write the recursive rules for these. So we start out with f of 0 equals a. And this should be an exponent. So what's a?
4.
4. And I'm going to write it underneath it. F of n equals
7.
R is 7 times.
F of n minus 1.
So to find a number in the sequence, we do 7 times whatever number came before it. Okay. Is this one growth or decay?
Okay.
Decay. So, but our rule is the same. F of 0 equals
9.
A. A is 9. F of n equals 1/3 times,
Sorry. F of n.
right. So 1/3 of the number that comes before it. So if we have, this pattern looks like 9, and then what's 1/3 of 9?
3.
And 1/3 of 3,
1.
and 1/3 of 1, 1/3 of 1/3,
6.
1/9. So what this thing is saying is to find this number, we take the number before it and multiply it times 1/3. That's what that pattern is saying. Okay, these two are in your journal. I want you to take a second and try both of these. I'll pause the video and then we'll check your answers. So you're doing what we just were trying on these two. And you're going to do it on these two that are in your journal on page 31. So here's your two answers for these. This means that the first number in the sequence is 2. And this means to find every other number in the sequence, we do 6 times whatever came before that number. Okay, this says rewrite each function to determine whether or not it represents exponential growth or exponential decay. So you're looking back at those models that we wrote that look like this. Okay, one looks like that, and one looks like this, growth or decay. So if it's plus, it's growth, and if it's less, it's decay. So we can tell if it's growth or decay just by looking at this number right here. Is this number greater or less than 1? So it is decay, and this one is greater than 1, so it's growth. Okay, so they're asking us to rewrite it like this. Y equals A, which is 100, times 1. Is this going to be plus or minus? Minus. And 1 minus what gives me 0.96? 0.04. So what is R? What's the rate of change? Here's R. 0.04 or 4%. I'm not sure in the book if they want you to write it as a decimal or a percent. You'll figure it out. And then for this one, we would have Y equals, what's A? 1. And this is 1, is it plus or minus? Plus, because that number is larger. What did we add to 1 to get 1.1? 0.1 to the t minus 3. And right now we're ignoring what the exponents say right now because they don't have an effect on what R actually is. So what is R for this one? 10%. Okay, the two that are in your book, 8 and 9, I want you to do the same thing for those two. I'll pause this and then we'll check. Okay, so for yours, Y equals 3 times 1. Did we add or subtract from 1 to get to 1.25? We added. How much do you add to 1 to get 1.25? 0.25 t plus 4. So R is 0.25, which is 25%. So that's got a 25% rate of increase. For this one, f of t equals, our A is a 1, so we can write it there or not, it doesn't matter. And this is 1. Did we add or subtract to get this? We subtracted 0.56. So R is 0.56, which is about 56%. Okay. Because it's not, R is not negative, R is just the value.
Okay.